Thank you for attending today. So our presentation is about disentangling object graph representation in the latent space of an artificial neural network toward creating brain-like affordances for machines. So if I want to really quickly go through the idea behind the research is that, so in the human sensory motor cortex, when you observe using methods like EEG, you see that when people are planning the grasping of different objects, there are representations being formed in the sensory motor cortex that correspond to specific object types. So if the object requires like a precision grasp, that would activate a different area of the brain in comparison with the place that would require a power grasp, which is using all your fingers. So there are distinct representations for the hand in the brain in response to each different object. So we were trying to see if we can replicate or observe a similar pattern in artificial neural networks that would distinguish the hand shapes for different object properties. So for this reason, we trained a conditional variation autoencoder on a very big data set of hand-object interaction, which is called HO3D version 3. Here you can briefly see a frame of the data set, which includes the hand, the object. For the hand, it includes the 3D joint information, hand position, translation. For the object, includes the point cloud of the object and the translation and rotation of the object. We put all of this in the variation autoencoder, and then we tried to cluster and visualize the latent space of this model. And as you can see, first of all, we realized that 97% of variation is explained by just the first 8 components of this, the principal component analysis. And then we realized that in later principal components, specifically 5 to 8, there are distinct patterns and clusters forming in the latent space that correspond to each object, and they're separated by the object type. And then there are some overlaps between the objects that are similar to each other and would require a similar type of grasp in comparison with the objects that are further away from each other. And so in very short, these findings can have profound applications in high-level motor planning and abstract reasonings to control humanoid robots, because we have a lot of degrees of freedom. And if you want to plan the motor actions in this the pixel level or joint level, it's going to not to be able to do it in a real-time manner. But if you can plan in these abstract representations, it would provide a way faster way for decision making and motor action planning. Thank you very much.
Any questions? We have still time for one short question, but if you're interested in any of those projects, feel free to grab them during the coffee break or after the workshop. So, okay.
Thank you.
In terms of the grasping, have you modeled only humanoid hands, or have you modeled also hand?
No, in this work we used the human hands because we didn't create the data set ourselves. We used already existing data set called HO3D version 3. But yeah, of course, the plan is to create to implement this in a humanoid hand. So yeah, that's the next step of the project. Yes.
So next we have Samir Bhatt for the title Neuromorphic Phase Detection of Human Hesitation in Self-Correction in Video Streams.